Hey folks, let's dive into something both mind-bending and downright warm. Literally. Ready? What if I told you that just by accelerating fast enough you could somehow warm up the space around you, or experience it as warm even in the depths of icy, empty space? Does that sound completely outlandish? Well, buckle up, because today we're exploring the Unruh effect, an incredible concept at the fascinating intersection of quantum mechanics and relativity. Okay, so what's the big deal with the Unruh effect? Let's break it down in a simple way before ramping up. It essentially states that an observer in accelerated motion, imagine, say, a rocket speeding up rapidly, will experience the vacuum of space as if it's glowing with thermal radiation. So, in essence, acceleration creates heat from empty space. It's kind of wild, right? And counterintuitive? To understand the basics here, picture yourself standing still in calm, empty space. From your perspective, you're surrounded by nothingness, which we call a quantum vacuum. In traditional physics, classical vacuums are described as empty, fully devoid of particles. But in quantum physics, this vacuum isn't truly empty. It's buzzing with temporary virtual particles that exist and annihilate almost instantly. Normally, this activity is invisible to someone at rest or moving at a constant velocity. But here's the kicker. If you accelerate, those virtual particle pairs present themselves differently to you. Now here's where relativity enters the story. Einstein's special relativity tells us that motion is relative. Different observers can measure various distances and times for the same event based on their motion. The Unruh effect demonstrates that not just distances or times, but even the very nature of the quantum vacuum depends on how you're moving. So, while someone in a stationary frame might see quiet space as perfectly cold, an accelerated observer would perceive it behaving like a warm, glowing thermal bath. That, my friends, is the Unruh effect in a nutshell. It's like space itself changes its behavior depending on whether you're standing still or hitting the gas pedal. But you're probably wondering, how warm does it actually get? Great question. The Unruh temperature is proportional to the observer's acceleration. This means that technically, as you double your acceleration, the temperature you perceive doubles. The formula typically used to calculate this temperature is T equals ha, 2 pkab, where h is the reduced Planck constant, a is acceleration, c is the speed of light, and kb is Boltzmann's constant. I know, equations aren't everyone's favorite snack, but look at it this way. This formula does nail down the relationship pretty clearly. Here's the catch though. For everyday accelerations, the temperature you'd perceive would be so close to absolute zero that it's undetectable. To notice this thermal effect, you'd need insane accelerations that dwarf anything we currently achieve with human technology. This is where many researchers get that intrigued, squinty look while leaning over their chalkboards. When studying systems involving both acceleration and quantum mechanics, like black holes or even early universe cosmology, the Unruh effect dovetails beautifully with concepts like Hawking radiation. You've probably heard of Hawking radiation. It's the thermal emission theorized to arise near black holes due to quantum effects. There's a strong conceptual link there, because both phenomena emerge when you intersect relativity and quantum fields. Now let's transition to the advanced stuff, the part that genuinely makes physicists scratch their heads. One big ongoing debate is whether the Unruh effect is something physical that could, say, be measured directly, or if it's fundamentally a kind of interpretative feature of quantum field theory. Attempts to measure it experimentally are tricky since the accelerations required are astronomical. Realistically speaking, experiments have focused on indirect analog models, like using electromagnetic fields to mimic quantum vacuum conditions. And that's opened a new question. If we can reproduce its effects in a simulated environment, does that mean the thermal perception would be just as real as observing it in accelerated motion? And here's an even thornier topic. The connection between the Unruh effect and entanglement. Some researchers have proposed that accelerated motion can disrupt entanglement and even lead to decoherence, which has massive implications for quantum computing. Others argue that the Unruh effect pushes us toward a unified framework, merging quantum mechanics with general relativity. This thing? Yeah, it's kind of a Pandora's box of questions. Okay, but what does this mean for the bigger picture? This effect underscores that our universe behaves not just differently, but entirely incomprehensibly when viewed through extreme frames of reference. Seriously, the idea that acceleration can tilt your perception of space into something entirely foreign is a cosmic statement about how deeply interwoven quantum and relativistic effects are. I hope this blew your mind, or at least warmed it up, in Unruh effect fashion. Since our channel is brand new, I'd love your thoughts. Subscribe if you're excited to keep exploring cutting-edge science like this. And as always, stay cruised, stay hyper-focused, and remember, the universe is remarkable in ways we're just beginning to see. Bye for now.